Okay, welcome to week 5, I think it is, of Robot Systems Programming. This week we're going to, this last week we had a busy week getting the EduMip up and running and writing an URDEF for it and understanding how URDEFs work with things like RViz and robot descriptions. There experiences that you'd like to share with the class of things that worked or didn't work with this last assignment? Any complaints? One of the things I noticed this last week was that some students came to me with questions which were the answers of which were found in the tutorials, and so make sure that I'm pretty careful about what tutorials I assign, and I tell you to skip some and do others. And if you don't do all the tutorials, then when you get to the assignment, it may not be obvious how to actually do the assignment. But if you do all the tutorials, when you get to the assignment, it should be immensely obvious how to do the assignment, because you've actually done all of the steps individually in the tutorials that are required in the assignment. And notice that, for example, this week we're on Module 5. Let me get the light over here. Let me know if you want me to close those windows, if that's bothering anybody. So this week we're on Module 5, week of February 27th. We're going to work with Gazebo, which is a physics simulation. It's a physics engine, and it was something that spun out of ROS and has become a freestanding thing. Thank you. Yep. Thank you. So it should have been in my bag, but they weren't. Thank you. Appreciate it. Tyler, did you want to say anything to the class? I see you get some spare parts.
No, I was just, a few students needed some stuff, okay. So I was just dropping off the start class.
Okay, good. Thank you so much. It was pretty awesome office hours you just had. In this week's assignment, Module 5, here, the topics are going to be Gazebo and SDF and worlds. So an SDF is a data format that it grew out of URDEF, and basically think of it as URDEF plus additional physics stuff like coefficients of friction, coefficients of restitution, mass, moments of inertia. So the things that you need if you're actually going to do a physics simulation. RViz is a data visualization engine. It doesn't know anything about physics, doesn't know about force, doesn't know about gravity or any of that. It just visually represents data that you spray at it with topics, and it has different visualizers for visualizing a lot of standard topics such as transforms and robots and things like that. And Gazebo, in contrast, is a real physics engine, and it will actually simulate the physics of your robot in the world. Before I get started, I want to thank you, Tyler. We'll have some audio. I wanted to do a robot out of week, continuing our tradition. And this week, in my laboratory over in the lab in Krieger Hall, 3 engineers from the Woods Hole Oceanographic Institution are working. And for those of you who don't know about the Woods Hole Oceanographic Institution, Woods Hole Oceanographic Institution is a private research institute based in Massachusetts, and it's one of the premier oceanographic institutions in the United States. It has 6 departments. It has a graduate program and no undergraduate program. And Woods Hole has been historically, for over 50 years, one of the lead, at the forefront worldwide of developing new technology for ocean science. In fact, just about 53 years ago, they launched a submarine called Alvin, which you may have heard about. It's the world's most successful oceanographic submarine. And the submarine Alvin is still operating today. And I've been collaborating with Woods Hole with the Department of Applied Ocean Physics and Engineering for about 25 years, and we've built a whole bunch of vehicles together. And this week I sent you around a seminar announcement that one of the engineers from the Sentry Group is going to give a seminar at noon on Wednesday, Ocean Science with the Autonomous Underwater Vehicle Sentry. And so, Ian is one of the engineers who's working in my lab, and what they're doing is they're taking the control system that has operated Sentry for the better part of a decade, and it contains a lot of code that was developed here in my lab with my students and with my collaborators at Woods Hole. They're reinventing a new control system based upon ROS, and they are planning to take it to sea in about a month and a half. And so it's a pretty exciting time for us. And this is if you Google Sentry, it's got its own Wikipedia page, and this is the Woods Hole Oceanographic Institution page about Sentry. It's an autonomous vehicle. It's about that big in comparison to a person, so it's close to 3 meters long, 2 meters tall, and about 1 meter wide. And it's got 4 articulated fins. You can see 2 on each side. Right now they're positioned vertically for launch, and each fin has a motor with a propeller on it. The propellers are thin. They're about this long, 3/4 of a meter long. And let's take a look at a video. An animation of Sentry doing a multi-beam hydrographic survey of the ocean floor.
Sentry, a fully autonomous underwater vehicle, nearly the size of a small car, is designed and operated by the National Deep Submergence Facility at the Woods Hole Oceanographic Institution. Since becoming operational in 2008, Sentry has been utilized by numerous ocean scientists from institutions across the United States and around the world, as well as other organizations, including federal agencies, corporations, foreign governments, and philanthropic organizations. Sentry is a part of the National Deep Submergence Facility, a joint venture between NSF, NOAA, and the Office of Naval Research. NDSF provides easy access to the deep ocean for scientists with a negotiated federal day rate for assets such as Sentry. In addition to its primary role as a tool for scientific investigation and exploration, Sentry is often applied when researching problems of societal importance. The 2010 Deepwater Horizon oil spill in the Gulf of Mexico required swift action to determine how and where the oil had spread, not just on the surface of the water, but also beneath. Multiple surveys were performed by Sentry to track and locate subsea hydrocarbon plumes and to obtain maps and images of deep-sea biological communities for follow-up observations. In April of 2016, Sentry participated in the search for the missing data recorder of the sunken cargo ship El Faro in more than 15,000 feet of water. The information recovered from the missing data recorder and the detailed maps created of the wreck site have provided investigators with additional tools for their analysis into why and how the ship sank.
There's an extremely broad range of applications of AUVs, anything from finding a lost object, such as the El Faro voyage data recorder or the missing Air France flight, but more typically it would be something along the lines of studying an area of the seafloor, at least the way that we work in our primarily science endeavors.
Sentry is a flyaway system that can be transported around the world and installed and deployed from multiple ships of opportunity.
Century packs into two 20-foot containers and moves by land, sea, or even commercial air cargo. We immobilize into that ship very fast, typically in 2 to 3 days, and then be ready to conduct science operations. We have invested an enormous amount of engineering design effort in optimizing Century's ability to work in the water at the same time as other assets.
Century is designed to work alone or in close coordination with other scientific instruments. Century routinely conducts simultaneous operations with ROVs, CTDs, dredges, net samplers, coring systems, towed cameras, and others. This significantly increases the efficiency of ship use and can provide a more synoptic view of the study area.
Many of the most interesting areas of the seafloor are actually quite rugged areas. They involve volcanic features or seamounts or canyons that are very difficult for a conventional AUV to operate in. And what that means is that if you want to collect your data very close to the seafloor in there, especially for things like images, you need a very novel approach to your AUV, and that's what Century provides.
Century has a unique shape. The double hydrofoil body allows Century to move efficiently, both vertically and horizontally through the water with a very high degree of inherent roll stability. Century's articulated wings allow the vehicle to fly over the seafloor while maintaining a controlled speed of up to 2 knots. This design allows Century to effectively survey steep terrain and near-bottom environments for extended lengths of time. The high stability of the vehicle improves sonar performance, which results in better data products.
Century collects a wide variety of standard data products. Probably one of the most common is our bathymetric maps, which we make with our multi-beam sonar. We can vary the resolution. We collect sub-bottom sonar data, which is a choke profiler. It's able to actually see the different layers of the sediments and bounces off a rock quite nicely so that we can actually see the depth of the sediment over the top of the rock. We carry a standard three-axis magnetometer view of the seafloor. And together those give you...
To support Century's usability, past special applications include mass spectrometers.
To very advanced communication.
NDSF staff can help you understand the vehicle, craft your operations plan, and make sure your proposals are successful.
Great music. So Ian, Dr. Ian Vaughn, who's one of the Century group members, is going to give an overview of Century and talk about some of Century's greatest hits that it's done in scientific surveys, as well as I think they're going to probably brag about some of the other kinds of work they've done, such as finding the El Faro. So a pitch for Ian's seminar at noon on Wednesday. Okay, this week you're going to learn how to use Gazebo. Yes?
How does it localize itself?
Well, good question. GPS doesn't work underwater, and so it's easy to figure out your depth because you can measure pressure very accurately, and we understand. And if you measure physical properties of the seawater, then you can understand how the density varies with depth, and so you can very accurately calculate your depth if you're careful about knowing the water column. Heading, pitch, and roll, it knows because it's got a north-seeking gyro compass that measures the local Earth's gravity vector with accelerometers, and it measures. It has angular rate gyros, and with that, it measures the rotation of the Earth, and it can find true north to within about a couple tenths of a degree, and local roll and pitch within about it's like 100th of a degree. So it's actually using gravity and the Earth's rotation to do that. It's what's called a true north-seeking gyro compass. That's a whole story in itself, but it's good magic. And then X and Y are much harder. And so we typically use some combination of acoustic techniques for measuring X and Y, either absolute X and Y position by measuring time of flight from known beacons, or local displacement where you have a Doppler sonar and you can measure the vehicle's velocity and integrate and get displacement over time.
So wouldn't the error add up as it goes?
Yeah, so you need to have corrections. So you need to have absolute corrections to the vehicle. And you can do that. There's a couple of different ways that you can do that acoustically with time of flight, acoustic ranging. So I don't have time to go into all the details, but there isn't any silver bullet for underwater vehicle navigation. You end up using a variety of sensors. And to actually get, and X and Y are the hardest things. And I've spent a good part of my career essentially working on various aspects of that problem. Any questions? Okay. All right, so back to this week's class. So when you read Gazebo overview, Gazebo API, and the SD format specification. The history of Gazebo is that, so before there was Gazebo, there was Player and Stage, which was software that Brian Gerke wrote when he was doing his PhD at USC, and he wanted to have a 2D simulator for having simulated robots running around in a 2D world, so that he could test navigation packages in simulation. And Brian graduated and moved on to Willow Garage, and he headed up the project to develop a 3D version of a simulator, and that's what we now know as Gazebo. It started out as as one utility in the ROS ecosystem, quickly became very widely useful, and so it split off, and now it's a freestanding software, open source software project that still sort of runs in parallel with ROS and still interoperates with ROS, but it stands on its own. And I'm not sure what's wrong with that link. So I asked you to do a bunch of tutorials. Please do the tutorials before you try to do the assignment. I'll step you through the tutorials today. So the Gazebo, we're using Gazebo version 7, and notice that, for example, in Gazebo version 7 tutorials, bless you. That's weird. This is not going to be a very interesting class if this keeps on like that. Let's see what we can do. Somebody's brought down the Gazebo website. Let me see if we can get to it through Hopkins any differently. Nope. Okay. Well, this is not going to be a very interesting class. While we wait for that to come up, let me not depend on the web, but let me just point out that if you go to this tutorial site, it lists dozens and dozens of tutorials. And the tutorials are grouped, and so there's a group called Beginning First-Time Gazebo Users, and it has 3 or 4 tutorials under it. Overview and installation. Skip this because Gazebo is already installed when you install ROS. Do the Understanding the GUI tutorial, and skip the Model Editor tutorial. And what the here we go. So this is an email from Ian over in the lab over in Krieger Hall. This is the Johns Hopkins University remotely operated vehicle. This is the ERDF of that, and this is the ERDF of Doppler sonar. And this is a track line. They've been driving the vehicle around in the water tank, and this shows the 4 beams of the Doppler sonar. So see, ERDFs can be useful. Get rid of that. There's 2 ways that you can call Gazebo. You can call the standard Gazebo, so we can say which Gazebo, and it's in user bin Gazebo. That's the one that you'll use for the first several tutorials, but it's not the ROS version of Gazebo. To run the ROS version of Gazebo, you'd say ROS run a ROS launch. ROS launch, Gazebo ROS, and then you'd give the name of a world. So for example, ROS launch, no, let's just do ROS, let's run Gazebo. Gazebo crashes a lot. It always has. It's not as bad as it used to be, but don't be surprised when Gazebo crashes. There we go. Third time, try. All right, so this is the Gazebo world, and there's not much here except it's got a very simple, this is called empty world, and it's got a ground plane. Z is up, this is X, red, Y is green. If you hold down your left button, you can drag things around. If you hold down your middle button, then you can, right button lets you zoom in and out, and holding down your middle button lets you tilt. It's not working very well. And the controls are fairly self-explanatory. This is the world, and we can click on physics and find out what our physics properties are. For example, gravity is minus 9.8 meters per second. There's a magnetic field, and so on and so forth. We can insert objects into the world. Make this full screen. A simulation is running down here. It's simulating the physics. There's nothing in the world, so the physics simulation is pretty simple. It's simulating a real-time factor of 0.99 real time, so it's simulating essentially it can simulate in real time. The simulated time here is 1 minute, 24 seconds, and so on. The real-time iteration and the updates of the image frame per second is about varying between about 30 and 60. And these are different models, and the tutorials will walk you through models. So for example, if we want to insert a Jersey barrier into this thing, then here's the Jersey barrier. I can put that in there. Maybe I want a gas station. I can put in a gas station also. And I can put a Pioneer 2DX robot here. And so these are all objects that are sitting on the ground plane right now. And if I am evil and I mess with gravity, which I am, and so gravity here is minus 9.8. Let's make gravity plus 0.1. The things that aren't attached to the ground, like mobile robots, start floating. Minus 9.8. Bonk. And so you see that it dropped down. The buildings didn't fly because they're not mobile and they're fixed in the world, but the mobile robot is not fixed. And when it blammed down on the ground plane, then the coefficient of restitution and the impact and the contact model governed its behavior. So we've got a real physics model going, and this is the Pioneer robot right here. We can introspect a little bit into these things. The right-hand panel is a little hard to pull out sometimes, but if I select this robot right here, get the robot selected, then, come on, bugger. Then I can find out about properties of the robot model. And you're going to make the SDF file, you're going to make an SDF file from your Zacro or ERDF file, which will make a physics-based simulation for your robot. So that's the basic user interface. You can also insert sort of canonical objects, like I can insert a cube here or a sphere to become part of your world. And what we'll normally do when you're doing testing is you'll normally have a launch file which will launch Gazebo, and it will load up a world which has whatever features and whatever robot you want to have in your world. These tutorials will step you through how to construct the model files for robots, so a robot model file, and the world file, and the world file consists of a whole bunch of objects that are being simulated. There we go. So the website's back online. That's good. And so picking up, so Gazebo version 7 tutorials, and then so you can see that there's, oh my God, there's a whole bunch of tutorials. Where do I begin? You're not going to do them all. Do the ones that I've selected for you, and do them in that order. And so you want to do overview and installation. You can look at it, but don't do anything because Gazebo's already installed for you when you installed ROS. We're using Gazebo 7, and so these beginning overview and installation, skip the model editor, and I've asked you to do understanding the GUI. You can just look at this, and basically that understanding the GUI explains what I just explained to you, left panel, right panel, that you can insert stuff from the world, undo, redo, and the bottom toolbar, and menu. And mouse controls, so drag and pan, zoom in, zoom out, and middle button should rotate. It was it wasn't rotating properly for me, so I'll have to figure that out. Next tutorials I want you to do are getting started. So going back here, we want to do this set of tutorials here, getting started. And so getting started, you can see what happens. Getting started is selected just a few things. And I want you to skip install and do quick start, components, architecture, and screenshots. This won't take you very long at all. So quick start, you run Gazebo, and I'm going to run Gazebo, and I'm going to load a Pioneer 2D world, paste. Gazebo crashes a lot, and there's an annual conference called ROSCON, and at ROSCON the developers of various packages talk about the greatest and latest version of their packages and the new features. And whenever there's a Gazebo talk, there's always a question from the audience. Usually the first question is, why does it crash all the time? And that's one of the problems with giant open source software packages, is that there very often aren't the resources to really track down some of these sort of startup bugs. And Gazebo is got this annoying habit. Okay, so this talks about the fact that Gazebo is a simulator. It actually consists of two different programs that run: the GZ server, which is the physics engine, and the GZ client, which is the front end that displays. And sometimes, if you're doing a big physics simulation, you run the GZ server on your 12-core machine that's got 128 gigabytes of RAM, and then you run the client on your local machine, because the hard compute stuff is done in the physics simulation. Gazebo can support several different physics engines, including ODE, Open Dynamics Engine, and Bullet, and several others, and ODE is the default. Gazebo components. So it basically talks about the fact that there are world files which specify the entire world. Models are things that live within a world, and a world file will populate a world with several models. And then there's some environment variables that you can use. And on a ROS version, we don't have to set a lot of these things because we'll just use the ROS environment variables. And it talks about plugins and Gazebo architecture. Just breeze through this. It talks about the basic components of Gazebo, that there's a communication library, a physics library, a rendering library, and a sensor library, and a GUI. And then, last but not least, how to get a screenshot with GUI. You click on the little camera in the upper right-hand side. And so that's the getting started tutorials. And then build a robot tutorial. This is where you're going to spend your time. You're going to spend your time in build a robot, build a world, and connecting to ROS. These three tutorials. And so in build a robot, here, you're not going to do all of these. Do these ones. Do model structure and requirements. Skip how to contribute a model, and do the rest of these. So model structure and requirements. So you can clone into your home directory a giant model database called Gazebo Models, and I've cloned it into my home directory, and so there it is, Gazebo Models, and you can see the Gazebo Models directory has got all sorts of things: Cessna aircraft, cabinet, a cafe table, cardboard box, a whole bunch of DARPA Robotics Challenge things, and a lot of robots and a lot of just stuff, lamp posts, trash cans, you name it, and houses, there's Willow Garage, submarines, and every one of these models something that lives in the environment. And this tutorial talks about the structure of a model. And basically, a model consists of, at minimum, it's a directory in the Gazebo models directory, and it will have materials which specify sort of colors of thing, meshes, which are custom 3D meshes, and other directories. And then the most important thing about a model that you'll learn in this tutorial is that model consists of a model config file. So a model, whether it's a house or a Pioneer robot or the robot that you're going to build, consists of two things. Consider a model config file, which specifies the version of the SDFs you're using, and depending on what version of SDFs you're using, you can refer to one or more different model file. By default, in this directory, the model directory, the name of the model, the preferred model, is model.sdf. And you can see that this model here we are in a RoboCup 3D simulated ball. So it's a simulated ball, and this is the model for the ball, model for a soccer ball. And the name of the model is soccer ball. It consists of one link, which is a soccer ball. It's a sphere with radius radius 4 centimeters, and this is the mass, moment, and inertia, and the mass is 26 grams. So this is a simulated ball, and this thing will roll around when you in the simulation when you whack it. This tutorial covers the structure of what it takes to pull a model into Gazebo, and a model will consist of at a minimum, materials directory, often a meshes directory, but it will have a bunch of other things as well. It might have a model SDF, so if the robot is articulated, it'll have an SDF, which is a glorified RDF, and it might have plugins. If your model has special things that it needs to simulate, such as you want to simulate a sensor that goes out and does something, or an actuator, then you'd normally have that in a plugins subdirectory of the model. And we're going to cover plugins next week. So I've asked you to making a model, make a mobile robot. What this tutorial will ask you to do is, making the model, skip how to contribute a model, do make a model. And I think I updated this. I thought I updated the website. Okay. So this tutorial is kind of useless. I'm going to annotate this and ask you to this one tutorial, build a robot overview, doesn't really do anything. They give you an example, but you don't actually physically, they don't ask you to do anything. So I thought I had already corrected that. So make a model, this one's kind of useless. Make a mobile robot, this is the one you want to spend time on. And I'm going to update the annotation on this one to say that there isn't actually an exercise in make a model. But make a mobile robot, that's something that we're going to spend time on. And so it asks you, this is the one that you really need to spend time on. Gazebo, by default, your own personal models, Gazebo will store in your home directory, subdirectory.gazebo, in models, and you can create models in this models directory and give them whatever name you want. They suggest you create a model called MyRobot, and you need to create a model.config file, which we just looked at, and you need to create a model.sdf file. And the SDF file is going to specify the geometry and physics of the model. And so what they ask you to do is to create in your Gazebo models directory, to create a directory called MyRobot, and create a model.config file, There it is. And it refers to model model.sdf right here. And model.sdf is right here. And this is my version of it, open with Emacs. And what you're going to do is you're going to start with a model that just consists of a box, and then you're going to add other things to it. And so this model, as I've constructed it right here, you add just a box for the mobile robot, and then you run Gazebo. And so we'll run Gazebo, and we're running, again, the standard version of Gazebo. The Gazebo by default comes up with an empty world, and we can say insert, and you can see that we can insert things from the web, from gazebosim.org, and so these are all the models that are available on gazebosim.org, and we can insert things from user-shared Gazebo 7 models, so there's a bunch of models there, and here's my own personal models, and here's my robot, so I can select this robot and it'll push a copy of my robot into the simulation. There it is. And so in this tutorial, they ask you to first create a box in the model, and you can see my robot consists of more than just a box. It consists of a box as one link, and then it consists of links which are two wheels, and then it consists of this sphere here, which is a caster, just to balance the robot that it drags around. So right now there's 4 links in this model, and if we look at model.sdf right here, a lot of this will be very familiar with you because it looks quite like an URDEF. So a link name is chassis. It's a box of certain dimensions, and it's got a visual representation and also a collision representation. Sometimes the visual thing will be a mesh with thousands of surfaces, but the collision for collision detection will be a simpler structure, so you can do collision detection in real time. And then the caster is a sphere of radius 5 centimeters, and then notice that it has not just geometry and visual representation, but it actually has friction. And I have many good friends who are computer scientists. I have a secondary appointment in the Department of Computer Science, so far be it for me to cast aspersions on the computer scientists. But couldn't you call Coulomb and viscous friction something other than mu and mu2? So those are friction coefficients, and these are also some poorly defined friction coefficients. So this is a frictionless caster. And left wheel and right wheel are links that are cylinders. And notice that we already know how to do joints. These are joints which connect the left wheel to the chassis and the right wheel to the chassis. So these are things that we're familiar with from our URDEF. And if you play your cards right, what you do is rather than doing an URDEF, you'll make a Zacro file, and you'll add to that Zacro file those things that are not needed by things like RViz, but RViz will ignore the extra things like inertia, friction, things like that. RViz will just not pay attention to it. And so you can use one file for both Gazebo and for RViz. And believe me, if you have a robot with more than 2 links and you try to maintain separate SDFs and URDEFs, it will drive you crazy because you'll never get them to match up. So best practice is to have just one file. And so in this tutorial, here's the simulation running again. They'll ask you to put this thing together, and you can select the model. You can drag out the right-hand pane. And right now, there's no, we don't have any plugins which will actually, say, control the wheels of this robot, but we will next week. But we can do it manually. So, for example, if I select the robot, I can see that I can apply force at the 2 wheel joints. And so I'm going to zoom out here a little bit, and I'm going to apply 0.2 Newton meters to the left wheel joint, minus 0.2, and then set it back to 0. So the robot's reacting to the torque on the wheel joint, and if I give it 1 Newton meter, it's probably going to go crazy. one of the wheels. So it's going to build up kinetic energy, and eventually it's going to tip over. So it's simulating the friction contact and physics of the system, and if we watch it long enough, the friction will bleed off the energy, and eventually it'll settle down if it doesn't tip over first. So, real physics. And so what you do in this tutorial is you can leave a copy of Gazebo running, and you can keep on reinserting the model as you add features to it, and you'll get different versions. So here's a model with one wheel and a caster, and a model with two wheels and a caster, and here's the previous one. And so you really want to go through this, and then they show you how you can attach a mesh. So this is a predefined mesh, and it's in the Pioneer 2D model. And so when you add that mesh to your robot, then it looks like this. Looks more and more like a Pioneer. And then they'll ask you to add a scanning laser, show you how to use a plugin to add a scanning laser. And here's the scanning laser plugin right here. And this is publishing the data on a ROS topic when we use the ROS version of the Gazebo. And they're going to step you through adding a few more links to your model so that you have a little gripper like this that can slide up and down, and the gripper can open and close. It's got some joints. And then they'll have you attach that to the front of your robot. There's your robot, and here's how to attach the gripper to the front. And eventually you'll get to something that looks like this. So here's a robot with a gripper attached to the front with a laser scanner on the front. Make a simple gripper, attach it to the robot. So you want to go through all these tutorials, skip the ones that I mentioned. I made an edit to this, but it must not have taken somehow. I must not have saved it. Make a model. This is kind of useless. It doesn't actually do anything, but make a mobile robot. This is really useful, and all the other ones are useful. So this, by the time you're done here, you'll really understand how to make a model, and you'll understand the guts of SDFs. Build a world. This does the same thing for worlds. So a world consists of a background and various fixed objects, as well as robot models. And so I want you to skip digital elevation models and do building a world, modifying a world, skip this one, population of models, and the building editor. No, I'm sorry. I want you to do build a world and modifying a world, and then skip these next three. Digital elevation model, population of models, and building editor. You don't need them yet. So do this one. It'll show you how to build a world. You'll populate shapes, and you can save the world. And you can build a world by just writing the code yourself, or you can build it by populating a world and saving it, and modifying the world. This talks about scene properties and physics properties. I've already shown you the anti-gravity trick. And good. So those are the basic ROS tutorials. Take a look at this friction example to see how to set friction properties. Friction is sort of incomprehensible. It's poorly documented in Gazebo, but this is a good place to start. And the last set of tutorials that I want you to do are connecting to ROS and ROS integration. And starting here, this is where you're going to start using the version of Gazebo which is designed to work with ROS. And I don't want you to do all these things. I want you to do ROS overview. And so this one, you can skip this because the correct version is already installed. And then installing Gazebo ROS packages, using a ROS launch, and URDEF and Gazebo, and that's it. So you want to do this one, this, using ROS launch, skip this, and do this one. So I only do the ones that I've mentioned. You can do the other ones, but you'll be getting ahead of where we're going. And so to install the Gazebo ROS packages, you need to do this. You need to install these packages. And don't install from source. And then using a ROS launch, this is how to run Gazebo with ROS. So for example, we can say ROS launch, Gazebo ROS, empty worlds.launch. So Gazebo ROS is the package. Gazebo ROS has several ROS launch files that are samples. You can see it's got elevator world.launch, rubble world, shape world, mud world, and range world. So we'll do empty world. Rubble world shapes. Now we'll do. So let's do Willow Garage world.launch. So this is a model of the building that Willow Garage had when they were developing ROS, and ROS launch, different worlds, and you can look at the world files. And this asks you to create a simple package where you create a world file and create a world that you can run with ROS launch. This shows you how to spawn models from the command line, and it shows you how to simulate the PR2. You need to install a package here. And exporting a model. And URDEF and Gazebo. This is the last tutorial I think I asked you to do. Yeah, URDEF and Gazebo is the last one. And so in URDEF you can add a Gazebo element. And the Gazebo element will be ignored by RViz, but it will carry things that will be read by Gazebo. And if you clone this package into your workspace and do cat can make, then you'll be able to run some simulations where you'll see they'll give you some examples of this is a Zacro file for simulating a Revolute robot arm, Revolute, and it points up vertically. And I think I have that loaded. So if I go to ROS Catkin workspace, source, and slash Gazebo ROS demos, right there. RRBot description, URDEF. Here's the Zacro file for the Revolute robot, and it's mentioned in the file. So this is a good example of a Zacro file for you to reference. You can see there's a bunch of Zacro macros, and there's a link 1, link 2, and link 3 connected by joint 1 and joint 2. And notice that this stuff all looks pretty standard. It's what we did last week. But then what's new here is putting a simulated laser scanner and a simulated camera on the robot. And also what's new here is this Inertia designation for the links. The links not only have visual representation and collision representation, but they have inertia. And for those of you who are comfortable with mass moments of inertia, mass is obviously the mass in kilograms, and the moments of inertia are in units of kilogram meters squared. And for those of you who aren't sure how to calculate that, then ask any mechanical engineer, and they'll show you how to do it. So these things don't need to be exact, but they want to be approximately correct for your robot, within a factor of 2 or something. When you've done all those tutorials, the assignment should be easy. And so what I'd like you to do is take the URDIF that you designed last time in the previous assignment that you handed in today. You create a new package called Edge My Robot Gazebo ROS. We're going to use this for 2 weeks. And it should have an URDIF, a launch, and a worlds directory. And I want you to, if your edge emip is not already a Zacro file, then I want you to make it a Zacro file in the URDIF directory. And your robot should have the things that you've already done, should have visual and collision, but it should also have an inertia specification. And these are similar to the instructions from last week. The wheels should have visual, collision, and inertia. And it should have 2 joints. And I've stipulated that when I did this, my wife and I have a little scale in the kitchen for measuring food, and it looked like the robot itself body weighed about 180 grams. It's not terribly exact. And the wheels, it looked like they weighed about 30 grams each. And so this is the section cut out of my URDIF file where I specified for the edge of the body the visual representation and the collision representation. And here's what's new. And there are standard formulas. If you have a uniform rectangular object of uniform density and total weight m, there are standard engineering formulas that mechanical engineers learn when they're sophomores for computing the principal mass moments of inertia. And so I opined that the moments of inertia, I use a standard formula to compute these things, and I set the off-diagonal elements of the moment of inertia tensor to 0, which is not unreasonable. If there's symmetry with respect to the center of mass, that's actually true. So they're pretty small numbers, and the wheels themselves are even less or smaller. So the wheel looked like to me it was like about 30 grams. And when you run the numbers for the moment of inertia for a cylinder that size, it was something on the order of 10 to the minus 5 10 to the minus 5, 1 times 10 to the minus 5 kilogram meter squared. So really small moment of inertia for that plastic disc. You don't have to use those exact values. You may calculate more precise values than I did. I would recommend that your robot have nice happy colors. These are the friction coefficients that I used. I don't really get hung up in that. And then I want you've already done a tutorial on creating a world. I want you to create a world file that will load up in Gazebo, and a launch file which will run Gazebo and let you simulate your robot. And so my version of this looked like this. ROS Cascade Workspace. So my package is called Edge My Robot Gazebo ROS. And there's a launch file. Next week we're going to add an RViz file. You don't need one this week. There's an URDIF file or a world file. So you're going to recycle this package for 2 weeks. And in the URDIF file here's my robot Zacro file. And we looked at pieces of that along the way. But it's really not that long, actually. It's got mass and things like that. And there's a worlds file. And my world looked like this. Pretty simple. It consists of a ground plane, a sun, and a gas station. I like having at least one object in the world so you can see when things move around. You get sort of a point of reference and a sense of scale. And then my launch file is this one that I asked you to do this week. You're going to do this launch file next week. My launch file looked like this. You can put your robot into the world in two different ways. You can include it in the world file, where it will be created in the world file. And what I did is I used the Gazebo ROS node called spawn rdef, and so you can dynamically spawn things by using these Gazebo ROS, and it'll do a one-time spawn. And so what this launch file does is it sets a parameter robot description. And how does it set that parameter? It finds in edgeunit my robot Gazebo ROS the file rdef edgeunit my robot.zacro. It calls the package zacro and filters that through filters this file through zacro. The output is an rdef, and it gets right into robot description. You've already done that, and then this launches the node. This basically launches Gazebo, and it includes the empty world.launch, and in addition to the empty world.launch, and the empty world.launch launches Gazebo. So that's where Gazebo will launch. You don't see Gazebo being launched in this file because we're including by reference this empty world.launch, which runs Gazebo, and then I'm also including the little world file that was that we created for this tutorial, and that's all we need. And then if I say ROS launch, this was edgeunit my robot Gazebo ROS, edgeunit my robot Gazebo Gazebo ROS.launch. Fire up Gazebo, and it will crash. Did you like that? Try that again. Came up this time, and notice that the robot has fallen over. It fell over while the simulator was coming up, and it only takes a fraction of a second. You know that when you kill your program, it goes donk. So it already dunked by the time the front end came up, so we didn't see it fall over. Models, edgeunit my robot, insert. And let's just do a little bit of playing around with this to convince you that physics is working. Come on. It eventually will come back, but sometimes, there we go. There's one more thing I wanted to demonstrate for you here. So the robot's already fallen down on its face. We can select the robot, and there's an invisible button on this monitor, but on other monitors you can see it for pulling out this right-hand thing. And I've selected, when I deselect my robot, I won't get anything here, but I've selected my robot so I can set the positions or velocities or force on joints. And so if I set this to 0.05 newtons, how about maybe 0.1? Whoop, that's a lot. Flipped over. So you can see I can interact with it, and right now it's balancing on its head. And let's go into the rdef that I created. So here's my robot, and so here's the edgement body. I put my reference frame from the edgement body at the bottom of the box, and so that means that I had to move the box origin up half a body length in the z-axis, so that it was stood up, and you did this, and the collision is there. And the center of mass is also at the same spot at the center of the box, and so I put my center of mass at the center of the visual box, which is half a meter in the z-axis of the link itself away, and its mass is 180 grams. What happens if I moved my mass to minus? So this moves the mass to be an invisible mass that's half a body length below the axle. So what's going to happen? Let's find out. Well, Gazebo crashes, that's what's going to happen. But after Gazebo crashes. So remember, there's no visual representation by default of inertias and masses. There is a visual representation you can turn on in Gazebo. We'll get to that. I don't find it very useful. So when we run this time, we've moved the mass. Mass is invisible, and it's half a body length below. Lo and behold, the edge of it is standing up. Right? So we're cheating right now. And next week we'll use a plugin which actually does closed-loop control to keep the robot stood up. And so this is essentially a pendulum on wheels, right? And you can't see the mass down here easily. And we can view joints center of mass, and you can see the center of mass is you were seeing the center of mass blob. The center of mass is a little bit below the surface. So you can view inertias. The inertias I don't find to be terribly useful. These are sort of crude representations. And you can make the vehicle be wireframe if you want. You can make the view be transparent. View center of mass. There's the center of mass. View contacts. These are where contact forces are being detected in the simulation. So you can introspect into what's going on. And make my view not transparent. Select the robot, drag out this window, 0.1. Whoop. So you can see my robot's not very stable. There's not a lot of damping, and I don't know where it went, but it's somewhere in the world. There it is. It's getting away. And there is a mode where you can attach the camera and it will follow the robot if you want. So, questions? So the goal this week is to make a package like I have described, which there's a world file you're going to add to your Zacro file, and there's a launch file. You won't have an RViz this week. That'll run Gazebo. Run your world, put your robot model in it, and you can mess around with the physics. But don't just jump on the assignment without doing the tutorials, or you'll spend a lot of time. If you do the tutorials, all of them, exactly the ones that I say, then the assignment should be easy. All right? Questions? Complaints? Any suggestions on how the course is going so far? Things that we could do differently?
Can we have more office hours?
We can. When would you, so we have things due on Tuesdays.
I think Friday will be good.
Okay. Yeah, we could have an office hour on Friday. What time of day is good for people? Later on in the afternoon?
Afternoon.
Yeah. Before dinner or after dinner? Okay. I'll be in big trouble if I take after dinner office hours on Friday with my boss, if you know what I mean. Let me find out what the TAs are willing to do, okay? And I can't guarantee that it'll be after dinner. And I'm working hard on recruiting a third TA. I'm hoping to get Rachel Hegeman to join us. She took the course a couple of years ago, and she and Ryan Howarth did one of the self-driving car projects with an electric car this big, with an i7 processor and a laser scanner. It was pretty good, and she and Ryan really, actually both teams did really awesome jobs with this. And so I'm hoping to bring Rachel on as a TA for the project part of the course, and I'm hoping that some of the teams will be interested in picking up the self-driving cars as part of their project. Any other suggestions? Yes.
We didn't get the email about the previous assignment, that means all was passed.
I can't hear
We
you.
didn't get any feedback about the previous assignments, that means our.
Yes, and I will give you feedback. I'm sorry, the fault is mine. And I gave, on the first two assignments, there were a few students that had some problems with their packages, and they didn't include, either had the wrong package structure, and I contacted them directly. If you didn't get an email from me, then it means you did well on the first two assignments. And I'm behind schedule on grading the third one, but the guys are going to grade the fourth one, so we hope to have 3 and 4 graded by the end of this week. And then I'm going to try to push out what your scores were for all of these. In general, people have been doing well, and for the few people who have bungled things in package structure or for reading source code, I've already reached out to them. Okay, any other questions? All right, see, on Thursday we'll mostly have a clinic class, and I might take 5 minutes to show some other projects from previous years to try to get you thinking about projects. I want you to start be thinking about projects now, because we're going to get right on them the first week after spring break. Okay? All right, I'll see you Thursday. Thanks, everybody.
Quick question. What are the meshes? You can find out all the meshes, right?
No, it's a render. It's something you make a render. A render. So they're calculated grids to if you want to have something. Yeah, textures. No, you want to have something that looks like a Ferrari. Then you're not going to do that by making objects. You're going to do that with a three-dimensional mesh.
A wireframe, and then you kind of put it on.
And texture map and the color and things like that. Hang on one second. Let me just get set up. Good. And let me pull up my. I'll be within 1 minute. I just got to pull up a spreadsheet.